Now this is actually from when the cats were bothering me, just the uncertainty principle. Just want to remind you, so last time, all right, so this is the uncertainty principle, which we proved from the Schwarz inequality. And the Schwarz inequality is the dot product of two vectors is equal to their absolute magnitude cosine of the angle between. So that's from high school, right? From the Schwarz inequality, we get to here. And so that's really it. On homework 5, though, you're going to have to do this for a time-dependent operators. So that's why, I covered it. It's a proof, right? Sometimes you don't really need to know a proof. It just, you kind of accept it to begin with. You actually are, because you're going to see it again on homework 5, when these operators are time-dependent. So just heads up on that. So that's why it's important. When I applied this to Sx and Sy, we know that the commutators, there's rules for commutators, you've seen those. So the commutator of Sx, Sy is minus Sz. Sx, Sz is minus Sy. If I had done Sz, Sx, it'd be plus Sy, IH bar, and whatever. Where I got confused yesterday, and unfortunately I'm still confused, is if I applied these averages really are for particular states, and what you get is 0 for this, for the S plus state, Sc plus state. You can't have an uncertainty for an operator when you're operating on its eigenstate, because by definition you know exactly what that state is, there's no uncertainty. For Sx, it's not hard to show that you get h bar squared over 4. And so I had a challenge for people to figure this out, but in the process, I tried to evaluate this for S plus, and I got 0, and I know that can't be right. So I wrote to some other faculty, and we're not sure. We think what happens is that, for one, this entity by itself is not 0. So often when you do the commutator, you get 0. The commutator is 0, not another operator. What I tried to do was, so I think that's why that this is not 0. So when I applied a state to it, I don't know that I should have done that. Or if I can do that, I should apply its eigenstates, which that would make this h bar squared over 4 times 4, 16, I guess. Anyway, so I'm still not quite sure what the hell is going on with this. But then I challenge you to figure out if this is finite, h bar squared over 16, I don't know, it's something. How can that be 0 and how can that be h bar squared over 4? Yeah? All right, you two, did you think about it?
I'm still where I was when I tried last time.
Okay, well, this times 0 is indeed 0, and that's not greater than, I'm not sure what the number is. It's not, anyway, so something seems wrong here. Now, again, so now you've seen it, so you can work on it too. The example is, if I apply a state such as e to the ikx, the delta p squared is 0, delta x squared is infinity. And so 0 times infinity is indeterminate because it's a well-known relationship that delta p delta x squared is greater than or equal to h bar squared over 4. So when you have this wave function, the momentum is perfectly known. This is an eigenstate of momentum. So the momentum is h bar k. So there's no uncertainty at all in the momentum, but the position is completely unknown, right? Because this is a wave that goes forever left and right. So where is it? Well, it's the absolute value, right? But this is defined everywhere. The absolute value of this thing is finite at any value of x. So you don't know where it is. So anyway, 0 times infinity balance out. That's why that's okay. So what I'm asking you is to apply that logic here. Why does this still balance out? Anyway, so blah, blah, blah.
It's different because the uncertainty principle comes from the experimental result, right?
What?
the delta is p square over delta x square, so there is an h bar by 4 that comes from the, that's an experimental result theorem, right? So we said that if you want to see the position, we need to put the light, then the momentum will not be equal to 0.
I'm sorry, I just didn't follow
So
you.
if you want to measure the position of an electron or an atom or something, you have to put a light or some kind of energy, then the momentum will not be 0, right?
Yeah, I mean, the uncertainty principle actually was designed to describe experimental, the fact that when you measure something, you change something. There's nothing wrong here, by the way.
Yeah,
Just so you know, nothing's here. It's your interpretation of this that.
It comes from the it's theorem derived from an experimental point of view. So we can apply the same thing into this one also. Yeah, it's fine.
Well, look, I think the answer is very simple. It's just an interpretation of what this is, and this is just a hint, right? So anyway.
So it's just that, like, okay, so you picked like z, like as your principal axis or whatever. So it has like complete certainty in what it is.
Yeah.
And then you have uncertainty in what x is, because when you know z, you have uncertainty in x and y.
I mean, right. I mean, if you do this, I mean, you should be able to do this by now.
It's kind of saying that we have components in different directions.
I mean, you know what Sx is, the operator. It's plus, minus, minus, plus. I mean, I think, didn't we work through this? So yeah, you can figure out this is h bar squared over 4, and this ends up being 0. And then the variance is this minus that. So, I mean, it's all perfectly calculatable. I mean, this should be really, really easy. That's why after your homework 3, I had you do a little bit of this to make sure that you're not completely floundering. Yeah. Anyway, so again, why is this number times 0 finite when any number times 0 is not? So this shows you that quantum, unfortunately, involves some interpretation, because mathematically this does not work, but philosophically it does. So this is why I don't like teaching quantum, because stuff like this happens. And this is actually okay. 0 times this number is technically 0, but at the same time, it's not. So, but it's because you have to interpret this, not just multiply it on a calculator, which is why this is very frustrating sometimes. So anyway, and again, I've given you a big hint here, why that works. And again, it's an interpretation. So, and I hope you can do this part here at this point. Yeah. So anyway, just think about that. It's an interesting problem. I'll write to Trinary and see if he knows what the solution to this is. So again, I know for a fact that when you evaluate these variances, you need to apply a state. It's just that I'm not sure if I'm supposed to do that for this. And the derivation says I can, but I have to admit I've gotten myself more confused than I ever imagined I would be. But I'll figure it out. I do want to point out one neat thing though. Another way to interpret the uncertainty principle is, all right, if you're an atom and atoms are round, and remember, we're doing silver, so neutral silver, it has a 5s electron, right? So 5s electron is got this weird angular momentum of spin. Now, since it's round, you know, a silver atom doesn't know up from down, right? That's absurd. So the spin angular momentum, which is, it's as though the electron is spinning on its axis like a basketball. Anytime something's rotating, it has an axle, right? An axle is the same thing as the angular momentum. If you want to represent the angular momentum of a spinning object by the angular momentum vector, it's the same thing as the axle of rotation, right? Now the thing is, the axle of rotation, I don't know where the hell it's pointing, right? It's an atom, it's round. I don't, you know, it's round. Okay, now how many data points would I have to tell you to describe where this axis is pointing? Remember, it's actually rotating, you know, if it's like this, it's actually rotating like that. Not that it's actually rotating when it comes to spin, which is a whole other thing, but anyway, how many data points do I need to give you?
If it's an
Every, all of them.
But then hold on, it's a
in a circle
vector.
is 2 point.
3. The answer is 3. You said 3, right?
Yeah.
You know why, right?
Oh,
Because it's a vector in 3 dimensions. You need 3 theta, r theta phi, right? Okay, but now notice that our state, let's say that would be Sx plus state. That's plus, right, it's very easy. Notice that how many data points do you have to describe that? I've given you a big hint. So
plus
2,
minus. Yeah.
right? Plus it's plus f square root of 2 plus 1 over square root of 2. You only have 2 data points. So for any vector, it doesn't matter whether it's s, x, it's any state. Any state only has 2 data points, right? Every state can only be represented by 2 data points because there's only an up or down state. So again, you see where you have why uncertainty principle exists? A vector requires 3-dimensional, I need 3 bits of information to know which of this way this damn thing is pointing, but my wave function can at most have 2. So there has to be some uncertainty. So it turns out, anyway, I just want to point that out. That's like one of the reasons these things happen. Remember that if you were a math major, you would have taken probably 1 or more statistics class. So when it comes to a projection, let's say that this is let's say that this is the plus state. Definitely the spin has a projection on the z-axis of h bar over 2. But the problem is that I don't know the projection onto the, I don't know what sx or sy are. So, so you would represent that by some kind of, right, so some kind of circle. So while I know that it's projection on z, I don't know how it projects on x or y. So technically, the way that these are often represented is as a cone. And anyway, so that's why you see that. So the projection, what is, here's y and here's x. So here's the projection, and then the projection, you can then project the projections components in x and y and know what the spin are in x and y, except that reality is, because you only have 2 data points, you never can really know with absolute precision where this vector is, so you never know what the projection on the xy plane is, and then you don't know what the projection onto the xy axes are. You can't know that. You only have 2 data points, and you need 3. And that's just one way that it manifests itself. Anyway, I just wanted to point that out. Look, I'm still just trying to review it after class is gone. Let's see, now, in terms of last time, it's just something I figured out a little bit. Last time, remember that we were talking about transformation of a basis representation. So I'm always saying that my cat draws a wave function, and I can say, oh, that wave function is 50% ground state of a particle in a box, 25% first excited state, 25% the second excited state. And mathematical tools allow you to know those numbers exactly. And now if I wanted to represent that as a particle, as a harmonic oscillator state, that's basically this process here. And, whoop-de-doo, it's a little bit of a mathematical, it's just like a thing you can do. What I like is you seeing new operators. You're seeing a new type of operator, not position, not momentum, not energy. This is a projection operator. And so it's different than what you've seen before. Its purpose isn't to return an eigenvalue that tells you where something is or what's its angle to the z-axis or anything like that. It, in this case, when we're doing spin, up and down, it ends up being pretty easy, right? So if you were changing, let's say you were changing, and this is on your homework, I don't quite remember exactly. If you're trying to change a Z representation to an X representation, it would be this. This would be the transformation operator. Right. So, I mean, it ends up, it's really easy, right? I hope you appreciate Dirac notation. It's really easy to work with. The other things to note are that the operator's times its adjoint needs to be 1. So now you're seeing an operator whose adjoint isn't, for Hermitian operators, the adjoint and the operator are the exact same thing. And that's true of all operators that give you things that are real, like what's your position, what's your momentum, what's your energy, what's your angular momentum. All of those, the adjoint and the operator are the same operator. This one isn't. This one isn't. You have to have this. And that's because this is called, this mathematical requirement, I guess, it's called norm preserving. So, so what happens is, of course, is that, alpha, which is 1, and that norm preserving means it's normalized. That has to be true if you re-represent it. If you re-represent in a different basis set, it's still better be a normalized state, which is very sensible, right? So, yeah, not much to say about that. And then, of course, this gives us a way to figure out what the adjoint is, which is 1 over the operator. And when I see things like this, it scares me, right? Because this is like maybe 1 over a derivative, and I'm not quite sure how to deal with that. However, I know that if this is a matrix, 1 over a matrix is really easy. You just Google inverse of matrix, and then there's some formula. A, B, C, D, inverse equals, A, B minus C, D, C, D minus A, B. Anyway, there's just some real simple formula for this, and you'll be doing that on your homework as well. I'm sure you get more complex. Okay, now I also went over the fact that this is actually, it's cool that you can do this, and you should do this just so you kind of get familiar. It's going to build up your ability to deal with Dirac notation, but no one does this. Because why would you? Why am I switching between harmonic oscillator and particle and a box wave functions? Why would I ever care to do that? The answer is I don't. Once I've figured out some basis that, I'm just going to stick with it. What you really want to do is take operators and convert those suckers. Those suckers you want to put in different basis representations. Now that is something that's done very frequently. So now I want to point out to you that this is a matrix element. So the reason I have to put it this way, normally when I represented an operator, I used 2 resolutions of the identity. And that's that's how I figured out how to represent it as a matrix. This gets a little bit more complicated. So for any particular KL element, like this one is, I call it KL, but that's 1, 1, right? You see the upper left. And then here's another KL, that's technically 2, 2, and that's 1, 2, and that's 2, 1. Anyway, so for any particular, to build this matrix element, tell me whether you're at 1, 1 or 2, 1, whatever. And then that matrix element is then this. Now here's our 2 resolutions of the identity that we normally use. So to build this matrix out, I just didn't want to have 4 sums. So that's why I'm just showing you what an individual element is. That gets real confusing. Like if I just look at my own notes, I get real confused with what I just said. Anyway, I just want to point that out. When I explain it, I hope it's, I hope you're following. Now and in general. But when I just look at my notes, I get more confused. So again, here is our normal representation of an operator matrix, where I have an operator and then I do 2 resolutions of the identity. So I've got A to the N, A to the M, and this is of course over all states in the basis set. So if this is spin, then there's like up, down, right? But if it's a harmonic oscillator, then there's a ground state, and there's an infinite number of excited states. Anyway, so again, this is the normal representation of a operator in matrix form. And all I've done is I put a B state to the left, which is actually an A bra with the unitary with the U matrix adjoint. A L. Okay. And then this B L ket, B to the L ket, elf state is just the transformation operator times the A to the L state. Okay, and yeah, that's really it. And the way that this is represented, and again, I cannot emphasize enough, you will be, any talk that involves any quantum mechanics, you will almost always see this representation. And the reason that it's important is when the operator, with your transformation operator, I can't remember if it's minus or plus. Okay, so that guy, that is the time evolution operator. When it does, that H is the Hamiltonian. And we're going to be dealing with this in by Friday of next week. And we're going to spend most of the rest of the class on this thing. It's terribly important to know that things change in time, right? I'm pretty sure about that. So what happened is, I'm just previewing. This is really kind of one of the harder things to get about quantum mechanics, is that we can think of states. We can think of states changing in time. So what I would do is I would apply this to some state, as I always do. And let's say that alpha is a eigenstate of the Hamiltonian, in which case this is what you get. So now what I'm doing is I'm allowing, now this thing is the alpha state evolving in time. So cool. Trust me, it's a little harder than this. Sometimes you can set these up to be easy, and that's what I've done in this case. I'm just previewing. Okay, so again, this is the alpha state, alpha ket evolving in time, which again, you can imagine, that's pretty freaking useful to know. However, it turns out to be, this ends up being a real pain in the rear end to deal with. So what you do is, remembering that quantum mechanics is all about applying operators to states to get answers. I don't really care about the states. I want to get information out of the states. So I can either evolve the states, or I can time evolve the operators, which ends up being way, way easier to understand and work with than evolving a state in time. So there's this one-to-one correspondence. When it comes to time evolution, I can let the states evolve in time. Well, while that kind of initially sounds intuitive, trust me, it isn't, and it's way complicated. Or you let your Hamiltonian evolve in time, you let the position evolve in time, you let momentum evolve in time, or whatever. And then you don't have to alter the states. The states are fine as they are, the operators change in time. And so anyway, that's also on your homework 5. So again, I'm going to be doing this next week. I just want you to go ahead and see it so that, as I always do, I want you to see things ahead of time and get as used to them as comfortable as possible. Okay, so now that I'm done reviewing, what we're actually here to do today, the book definitely, I'm hoping you're all reading the book. We're still on chapter 1. We're at like the last 10 pages of chapter 1, by the way. I know I needed to make a schedule about that, and I didn't because I didn't really know where I was going to be. So, continuous states. The revised version of this book is a little bit better about explaining this than the original. I actually have the original. The revised is a little bit better. That's the one you may have found that in the woods on the internet. And by continuous states, instead of plus and minus, we now get position and momentum. Right. Now, what the book does horribly is not really tell you what they're really doing. And this is, I've told you this a zillion times. X alpha, everything's alpha, right? This is a wave function, just like you've seen before, like we were dealing with at the beginning of the class. And you also see a little bit more about what the bras do. Kets are easy to understand. Kets are states. But the bras are always a little bit like what? You know, what do they do? This is one of the best ways to understand what a bra does, is to understand that sine pi x over L, e to the ikx, the stuff you're used to is this in Dirac notation. So anyway, so you're projecting onto the x-axis. Now, here's what I want to get to. The reason that this is way more interesting than it appears, you can do that. Momentum and position are just one over each other. They're Fourier transforms of each other. In fact, in solid state electronic structure theory, you don't look at wave functions in position because a solid, from an atomic standpoint, goes on forever. How are you going to plot that wave function when you want to look at atoms in a thing composed of 10 to the 20 atoms? You can't plot that, right? So for solid state electronic structure theory, you do this. For molecular structure theory, you do this. But they're the same thing, and that's what the point of this, what I'm going to show you now. So anyway, so that's a big picture about what this is. In the book, makes you think that you're learning something like way different. And sine pi x over L, right? That, you know, again, high school students can understand that, right? And this is just a representation. Now, some of the things you have to get used to is that resolutions of the identity, which, as you know now, are hideously important. That's how we do all our proofs. When we had, you know, this was plus minus for spin. The correspondence is this. Now, another thing to look out for, and I'm going to try my best, the book is obsessed with little dashes, and I don't know why. Sometimes, if I do two resolutions of the identity, then with X, I do need to distinguish one from the other, and then I would have like a dash or two dashes. But for the most part, I find the book's use of these little dashes, I find them insane. I mean, you don't need them. They don't mean anything, right? But the book just has them everywhere, like fleas on a dog. Anyway, I use the minimal number of dashes in my. When I'm going over things, I will try to make it really clear why I do or don't have a little dash. And again, the reason I have a little dash is if I do two resolutions of the identity, then I need to make sure that we keep track of what X corresponds to what X. Anyway, resolution of the identity for a continuous state is this. And I hope that's, I mean, I don't know if that really bears any explanation, right? I mean, you know, plus, minus, right? There's only two things there. But of course, from here to the wall, there's an infinite number of points, so you need an integral. Okay?
What is the practical sense of continuous states? Is it density of states? Or?
No.
A practical sense, like if you want to just find the wave function, portion of the wave function, like
well, what this does is that you know, spin up, spin down is fine, and spin for an electron is important. But there's other wave function problems, like particle in a box and harmonic oscillator and hydrogen states that are not just binary, are not just, you know, yeah, they have real coordinates. So what this really does is it allows us to use Dirac notation on things that aren't really all that amenable to Dirac notation. Dirac notation is great for spin. I mean, it's freaking awesome. In fact, I don't think you could really do it any other way. For normal wave functions, like undergrad level wave functions, they're not so useful. So there's some tricks here to be able to still use Dirac notation because I'm still going to be able to do some really kind of awesome proofs with it. But I need to have the toolkit. So you'll see here, I'll show you one or two. I'll show you one cool one here in a minute. Anyway, let me just remind you of how Dirac notation worked on. Okay, so for two different states, let's say that's plus and minus in our SC basis. That'd be 0. It's a Kronecker delta. If it's plus, then it's 1. If it's plus minus or minus plus, then it's 0. That's what a Kronecker delta does. So our new Kronecker delta for a continuous state is this. And again, you see my use of dashes is to distinguish which one is which. And I also try to be careful about this. When I write the bra ket this way, the delta function is bra minus ket. Now, in all honesty, it doesn't matter. I mean, I'm going to try my best to keep it straight, but the direct deal, the direct delta, only does things when the argument is 0. So you could say that x dash is equal to x double dash, or that x double dash is equal to x dash. It's irrelevant which one you call the other. But there is, you know, there are rules about how you should do it. So I'll try to follow them. But if I mess up, I'm sorry, but it doesn't matter. Okay. So anyway, now with this stuff in hand, let's go back and project onto alpha state that's always getting projected on. This is so weird. Today, when I wipe out the board, it's clean, and yesterday it wasn't. That's really freakish. Okay, so anyway, okay, for some God knows what state, let's project. Let us project. Okay, and I have a little dash, and I'll explain why. Again, it's a bookkeeping effort. Okay, so I've done a resolution of the identity. Now again, hopefully, now remember, this is like sine pi x over L. There's nothing crazy mysterious about this. It's a little funky how you deal with this though. What does this mean? Well, a ket by itself, remember that in Dirac notation, until a ket is projected into a bra, it's all really abstract. It only becomes meaningful when I have an inner product. And I think I mentioned that before, but now you're really getting, hopefully you're really getting it now, right? Okay, so I'm going to project this into the x state, right? I mean, it's like, well, wait, didn't I already do that? Well, let me just show you what happens. This is kind of cool. And now you see why I'm doing my bookkeeping. X dash, bookkeeping, x dash, alpha. Okay, now as I just said, this is Dirac, and let me make sure I follow the rules. Now you know a Dirac delta function eats an integral. Integrals disappear, and the other thing is, again, if I'm going to follow the rules, and if I do it right, here's how I keep this straight. This is a real biz knocker. This is how I keep it straight. Do the x's become x dashes, or the x dashes become x's? Which is it? Now again, you can actually just pick one. That's fine, but there is a little method to the madness, and it's kind of good if you have an algorithm than not. Here's how I do it. I look at this integral, and I see my partial. My partial is x dash, because that's how I resolve the identity. Now that means that I'm scanning over x dash. And I scan over x dash, and this damn thing gives me nothing. It gives me 0, so there's nothing going on, until x dash is equal to x. Right? Then the argument is 0. Then this turns to infinity over an infinitely narrow range. And anyway, so we've talked about Dirac delta functions. So what I'm seeing from here is, if I think about it, my x dashes need to turn into x's versus the other way around, right? So I hope that kind of makes sense. So again, I'm scanning over x dash, and this integral doesn't die unless x dash is equal to x. So what I'm going to do is I'm going to get rid of the integral, and that's the delta function, so that's gone. So every x dash turns to x. And so there we go. Look at that proof. I know that's kind of silly, but yeah, anyway. I want to point out another thing about this. In terms of how to think about this, and this one's really important. Here, I'll plot. I've been saying that these are wave functions. So here's x alpha is on the. No, that'll be too confusing. Here, let me. X alpha. Okay, so again, this is our sine pi x over L, and here's x, and well, maybe it's a nice little Gaussian. So that's e to the minus x squared. Okay, now this one's really important. When you look at this, you're probably thinking, because I've been saying it for too long, that this is a wave function, right? So this is like a Gaussian. However, I have to kind of backtrack on that a little bit. Don't think of it so much as a wave function, because see, the thing is, this wave function has amplitude over all values of x. I mean, that's how I drew it. But don't really think of it that way. What you really get, when you look at this thing, what you really need to do is think, okay, for x of 1, it's here. For x of 1.0, what's the amplitude? And that's what this is. This graph is really an infinite number of these, right? An infinite number of these where this bra is 0, 0.001, 0.002, 0.003, technically it's an infinite number of them. But again, so you really want to think of this bra here as being a very specific value of the x-axis. And again, I know that there's technically an infinite number, and that's why this is a little funky. But don't think of this as sine pi x over L. I know I just said that, but think of it as sine pi x over L expresses a giant table of numbers. And this is the x, the first column, right? And the wave function is the right column. Anyway, now that'll be more clear here in a second. So anyway, I'm just trying to set you up to think that way because of reasons I'm gonna show you here in a minute. So let me do some funky things here. This is kind of funky. I actually like this one, and sometimes I show when I do undergrad quantity. Sometimes I like to show this because it's kind of cool. It's one of the coolest things you can do with it. And remember, Dirac came up with Dirac delta functions because of one particular reason that, they thought this eigenvalue stuff is how things work. But let me ask you this. Let's operate on a wave function like I've been talking about pi x over L. I've been talking about this forever, right? Okay, eigenvalue equation. Operator, function, some kind of number times the function. And that has to work or you're doing junk, or you're speaking badly. Well, that doesn't work. The x operator is x. It's just x. No hat, I guess, right? Well, no, that's not an eigenvalue equation. Right? And how could it ever be? How could you ever have a function multiplied by x equals a number times that function? How could you ever get that to happen? Dirac figured it out. And the answer is a Dirac delta function. These are not the wave functions. These are not position wave functions. Dirac delta functions are position wave functions, and I'll show you that in a second. All right, so what I'm going to do is operate on what is the real wave function of x, right? And it's not going to be sine or cosine or e to the minus x squared. It's not going to look anything like that. Okay, now to figure this out, I'll resolve an identity. And again, bookkeeping. So I better have a different type of x, so I have an x double dash. And the resolution of the identity looks like this. Okay, then I've got what have I done? I think I made a slight mistake. I think I needed to, did I need to do that? No, I didn't need to do that. I didn't need to do that. Okay. Anyway, so I put the resolution of the identity up front. My notes are a little screwed up. Sorry about that. Okay, now, okay, so now by definition, we'll have the x operator act on this thing, and that means that these two have collapsed together. Now again, so this is operating on that, and by definition it spits out a number. And that's what I'm telling you. You've got to think of these things as specific points, right, in that graph. This isn't the x-axis. This does not represent the x-axis. None of these represent the x-axis. They represent singular, well-defined points on the x-axis. So if this x prime is the 1 nanometer ket, then spit 1 nanometer, right? So again, think of these kets as like, think of this wave function as a column of numbers, and the x's are the left column. Okay, anyway, all right, so now what? Now this guy is a delta function. Okay, and so now what? Now I've got x prime. I'm just rewriting the same thing, a little bit more meter. Okay, now I'm scanning over x double prime, and so the integral goes away, and every x double prime becomes x prime. So here's my x double prime, that now has become x prime due to the delta function. Look at that. See, the SOP worked. I actually could do it. I could do it. I could take the x on a state and return a number times a state. It totally worked out. I mean, it kind of makes your head spin. It's like hard to get it. I don't know. I had a hard time getting it in my head. Let's see. What else do I want to say? Yeah, not much else here. We're going to do a lot more with this, so if this gets a little head spinning, as with everything with quantum mechanics, it's a matter of doing it over and over again until you're comfortable with it. What's that?
Can you explain the last step on this?
Now again, so remember, a direct delta function, when you see a direct delta function, you better have an integral or it's garbage. The purpose of the direct delta function is 0 everywhere except where the argument is 0, in which case the value becomes infinity. Okay, but you're integrating over an infinitely high point, but it's also infinitely narrow. So this thing just basically destroys the integral. It destroys the integral except at the point where x double prime is equal to x. And again, which, do I write all the x primes as x double prime, or do I write the x double primes as x prime? Which is it? Either is actually okay, but if you want to stick to the rules, you're scanning over x double prime. And so wherever you have an x double prime, it becomes x prime. I hope that didn't make your head spin, but that's how it works. So the direct delta function, the integral goes away, and wherever you see an x double prime, we now write x prime. So it's unbelievably easy. So there you go.
Then the S prime is a constant number, right?
It's a constant number. So remember these states, these kets of position, this is the 1 nanometer ket, or 5 nanometer, whatever. And so when it operates on 5 nanometers, out spits 5 nanometers. Right, so that's why you want to just not quite look at this the same way as you used to. Okay, and then I have a bunch of other examples of resolving IDs and things that you're more familiar with. We'll have to do that next time. But this is actually if your head's spinning a little bit, this is actually really one of the easiest things. And it will become easy if we just do it over and over and over again, which is absolutely what we're going to be spending all week, is just resolving freaking identities over and over and over again, and you're going to get so used to it, and it makes everything so easy. You're really going to appreciate it. All right, we're on time. It's been amazing. Well, thank you.